What's up, y'all? Here today we're going to be talking about whole numbers as equivalent fractions. So just an understanding of like how whole numbers and fractions are equivalent, what those look like, what are pieces, how do we put them together, how do we write whole numbers as fractions, and so on. So let's just kind of play around with the little things that we know so far. One indication we've looked at in the idea of, I don't know, let's just say number line, and if it's cut into fractional parts, right? We've already thought about this part of how we label each section of this, right? This refers to 0 out of the 4 pieces. Here's 1 out of 4. Here's 2 out of 4. Here's 3 out of 4. And then this is 4 out of 4 because again, if we thought about that model, well, 4 out of 4 is all of it, right? And we can also look at this in terms of division, knowing that again, a fraction is a division problem. And we just read that division problem from top to bottom. And this just says 4 divided by 4, and that equals 1. So that's what background knowledge we have around that. But really what we want to start looking at is what happens when we actually have the whole number first, and how do we look at that as a fraction. So again, like if I had a number like 13, like how do I create an equivalent fraction? So previous knowledge of what we've looked at before, all right, like what we just talked about there, our first thought might be, oh, cool, well, 13, if I just make that 13 out of 13, well, that would be equivalent fraction. But that's actually not correct because, again, if we did math, 13 divided by 13 equals 1, and 1 and 13 are not equal. So we have to start thinking about, again, this relationship of fractions and division and how that can help us think about how a whole number would turn into, or convert, I should say, like let's use math terms, convert into a whole number. So I'm going to take a couple whole numbers and just plop them down here. Let's take 5, let's take 3, and let's do 13 again, right? And we want to start thinking about, well, what do we know? What does this mean? What is this piece? Well, for starters, we know all these numbers are larger than 1. So that could even go back to this idea that we've looked at before when we have fractions that are larger than 1, right? Like if I had 5 over 3 or 5 out of 3 or 5/3, we know that this is actually going to be larger than 1 itself. So we also then know that all of these will be larger than 1. Therefore, meaning if we write them as a fraction, then the numerator is going to be larger than the denominator. Okay, so that's a good first piece to think about. So then what would that mean, right? Again, if we thought about this as, oh, well, 5 out of 5, that again wouldn't work because remember, 5 divided by 5, which is what this says, is equal to 1. And we need it equal to 5. So that's not going to work. So let's play around a little bit. Okay, well, we know we have 5. So if I took this and thought about, okay, I have this 5, right, to equal 5 wholes. Well, what if then I put it over 1? So let's think about this checklist. First of all, the 5 is bigger than 1. So the numerator is bigger than the denominator. So that checks off the whole concept of a fraction larger than 1. So that works. And we need that because we're looking for 5. If we looked at this in terms of division and wrote this as a division problem, meaning that 5 divided by 1, well, if we did that math, if I took 5, right, if I took 5 things and I put them into one group, I have 5 again. So that actually checks out. So if 5 divided by 1 equals 5, well, then this is how I could actually write a fraction and a whole number in an equivalent way. And we could even model that now because, you know, I'm like, oh, let's do more about that. We could even model that to really prove what that says, right? If we thought about what that looks like as we've looked before with fractions larger than 1, well, here's a fraction larger than 1. what it says though, is if I model it, each model is cut into one piece. Well, there's one piece and this equals 1. So I would shade in all of that. But I need 5 of these. So there's 1. Right? There's 1. There's another 1. So that's 3. And of course, I'm going to run out of space. So this doesn't look cool. There's another 1. 1, 2, 3, 4. And 5. And again, each one of these is cut into one. It's like not even cut, right? It's just one hole. And I have 5 of them. And so you can see 1 plus 1 plus 1 plus 1 plus 1 is equal to 5. So that's the why of all of this. But let's just look at the basic how this works. When we have a number, I think 3 and 13 were my examples before, and I erased them because I got crazy about 5. We're just going to take that number, and if we put it over 1, it's a fraction and it's equivalent. It's the same thing. Right? So 13, oh, that's 13 over 1. Okay, 1,000. Oh yeah, well, that's 1,000 over 1. Oh, it's 6. Okay, well, that's 6 over 1. 23. Well, that's 23 over 1. So this is how we really just make equivalent fractions with whole numbers. And it does just work that way. So I know that can be a little confusing with what we talked about earlier. Well, what if I have 3 out of 3? Well, remember, 3 out of 3 is equal to 1 because it's a division problem. 3 divided by 3 equals 1 whole. But then you bring about that question, well, what if my number was 1? How do I write that as an equivalent fraction? Well, you actually could write that as 1 over 1. Because again, 1 divided by 1 equals 1. So really how this works is when given a whole number and I need to make an equivalent fraction, I can just put it over 1 and I'm done. So 6 as a fraction is written as 6 over 1. 3 as a fraction is written as 3 over 1. And again, we can prove this mathematically because this is a division problem. We read it from top to bottom. It says 3 divided by 1. Well, if I have 3 and I divide that 3 into one group, I still end up with 3. And the inverse proves that as well, because 3 times 1 is 3, right? That whole idea of doing the inverse operation. And then again, if I modeled this, and of course, you know I have to model it again, and we think about what this says, well, think about what this says. Pen, start drawing, please. There we go. 3 over 1. Well, again, if I'm going to model this, right, it says according to my denominator, I'm going to take my model and it's going to be one piece. So I don't even have to cut it. Now, according to my numerator, I need 3 of these. And if each one of these is equal to 1 whole, well, then this is 1 whole, this is 1 whole, this is 1 whole, and 1 plus 1 plus 1 is 3. So again, this is the why we can do all this, and this is just the blatant how. It's just straightforward. If I have the number 10 and I want to make a fraction, I just call it 10 over 1. So there you have it. Quick tutorial on that. If you have any questions, of course, you always ask because that's that math norm. Ask questions until things make sense. Also know that other math norm of answers are important, but they're not all the math. So how we explore math and how we do things like draw these models and explore and make mistakes and learn from those mistakes is a really cool math norm as well. So as always, we appreciate you and your time. Keep up the good work. Do not stop asking questions. Do not stop working towards this. And if it ever doesn't make sense, that's okay. That's part of math. What you need to do is ask those questions, practice it out, draw, and work on some models, and it will come together, we promise. Until next time, enjoy your mathematical journey.